Hello, our presentation is on novel music generation through artificial intelligence. Music has been and will always be a core integral part of human culture that has been with us from the earliest periods of human civilization and has grown into a great diversity of forms. It evokes a singular human spirit in its creation, and therefore it begs the question that can computers ever get as good as to capture this creative process? And this question has fascinated computer scientists for years.
Now, before we dive into the model straight away, let us look at some of the basic terminologies of music, which would help us understand the models better. Understanding the basic constructs become important when we plan to convert a music file into a machine-readable format. The term pitch describes highness or lowness of a sound. There are 7 notes, and each set belongs to an octave. These octaves are used to designate which pitch range the notes are in. A scale is a specific set of notes with which to create a song. Structurally, most music contains a melody, or a sequence of notes with a single instrument. A chord is a set-defined collection of notes played at the same time, producing a distinct sound as a group. Within a single time step, multiple notes can coexist, creating harmonic intervals. These notes can also be patterns between multiple contiguous time steps. Any model which creates small, non-connected subunits do not contribute to a sense of a coherent composition because of the connection between the notes and their higher dimensionality. To effectively model music, we need to pay attention to this structure. Now we move on to some of the classic approaches that have been tried and tested for music generation. One of the approaches that we will look at in detail is the neural networks. Automatic music generation dates back to more than half a century. Major contributions were made to symbolic approach. For example, a piano roll which specifies the timing, pitch, velocity, and instrument of each of the note to be played. Each captures a specific aspect of music generation. For example, melody, composition, or the human voice. Here are some of the major contributions that have been made to the symbolic approach. But from here on, we will discuss neural networks in music generation. The first thing that comes to our mind when dealing with sequential data are recurrent neural networks. The most straightforward way to compose music with an RNN is to use network as a single state predictor. With recurrent connections, it can use hidden layer activations as memory, and thus is capable of exhibiting temporal dynamics. In practice, however, RNNs do not perform very well. The reason for this failure is likely linked to the problem of vanishing gradients. This has many drawbacks. RNNs can store information of only the states before, which means that context extends only one generation back. In gradient methods, such as propagation through time, and real-time recurrent learning, error flow either vanishes quickly or explodes exponentially, making it impossible for networks to deal correctly with long-term dependence. As we had already discussed, there's no point in generating music which has no structure. RNN cannot be useful in music composition where the beginning of the song plays a role in the middle and in the end as well. Long-term dependencies are at the heart of what defines a particular style, with events spanning several notes or even many bars contributing to the formation of metrical and phrasal structure. LSTM networks solve the problem of a lack of long-term memory in regular RNNs. LSTM networks add a special kind of cell named memory cells. These memory cells consist of 3 gates: input, output, and forget. Input gates control how much data is inputted into memory. Output gate controls the data passed to the next layer, and the forget gate controls the loss or tearing in the shared memory. These gates contain sigmoid and hyperbolic tangent functions. The function of these memory cells is that they extend the memory of a regular RNN and allow the network to read, write, and delete stored information based on importance. This allows the network to store long-term memory, which is especially useful in speech recognition and music composing. It will help in recognition of melody structure and proper note sequencing as well. The LSTM is designed to secure information in memory cells, separate and protect it from standard information flow of a recurrent network. To pass, read, or forget information is performed by opening or closing the gates, akin to a neuron firing. This is learned during the training process. Gates are modulated by weight, that is differentiable, allowing for backpropagation in typical neural network learning fashion. The MIDI representative was selected because it offers a particularly rich representation in two senses. First, it carries characteristics of the music in the metadata of the file, like time steps. Second, it is a common digital representation which allows access to freely and widely available data. There can be multiple access to the LSTM model. The note access LSTM receives as input a concatenation of final output of the note access LSTM for the previous note, and the activations of the last time access LSTM layer for the particular note. The output of the final activations of the note access LSTM are then fed into a softmax layer to convert to a probability. The loss corresponds to the cross-entropy error of the predictions at each time step compared to the played node at each time step. Each node, therefore, has a time component from the time axis LSTM. This allows for understanding the temporal relationships for the particular node and for modeling the joint distribution of nodes in the particular time step. By joining the information from an LSTM focused onto the time component and an LSTM focus on the node component, the relationships between nodes is captured for each time step. By using this approach on each node in sequence, the full conditional distribution for each time step can be learned. LSTM node access layer computes the probabilities across all time steps. This provides a significant speed up when using a GPU to perform parallel computing. Now that the probability distribution is learned, sampling from this distribution offers a way to generate new sequences. Sequences are not known in advance. The network must project one time step in the future at a time. The input for each time step is used to advance the LSTM time axis layers by one step to compose the note in the next period. First, a sample must be taken while the distribution is being created. Each node is drawn into a Bernoulli distribution. This drawn value is then used for the input to the next node. This process is repeated for all the nodes, after which the model moves to the next time step. After training the biaxial LSTM, the model was used to create new musical compositions. A large and diverse dataset with different node and structural patterns was used during training. The goal here was to expose the model during training to a wide variety of patterns so as to encourage as much diversity in input as possible. Training such models posed some difficulties as well. One of the recurring difficulties encountered when training these systems is deciding on a representation of music. Designing an encoding for an RNN might start with a metaphor of text. The RNN is processing a sequence of states unfolding over time or space. But unlike text, a single moment in music can contain more than one symbol. It can be a chord or it can have combination of qualities that is best described by its components. There can also be long durations of silence, or states can have widely varying lengths. Even though training different LSTM networks to learn different structures does increase the depth and complexity to which the model can understand music, however, the architecture is not able to create a more diverse combination of notes. Another model design that would be effective would be generative adversarial networks, which have achieved remarkable progress in generating photorealistic images and as such should provide effective musical generation.
Now, a modern approach to this problem would be to pursue the non-symbolic representation, where we try to produce music directly from a piece of raw audio as a piece of raw audio. This makes the problem more challenging as the space of raw audio is extremely high dimensional with high amounts of information content to model. For example, a typical 4-minute song at CD quality has over 10 million timestamps. Thus, to learn high level semantics of music, a model would have to deal with extremely long range dependencies. Now, one way to address this long input problem is to use an autoencoder that compresses raw audio to lower dimensional space by discarding some of the perceptually irrelevant bits of information. Now, before we look into one particular example of such an approach, let us familiarize ourselves with some of the basic terminologies we're going to need. Now, what are autoencoders? Autoencoder is an unsupervised artificial neural network that learns how to efficiently compress and encode data and learns how to reconstruct the data back from the original reduced encoded representation. They work by compressing the input into the latent space representation, also known as the bottleneck, as we see in the middle here. Now, the purpose of doing this is since the dimension of the bottlenecks are smaller than the dimension of the input layer, only the most salient features of the system remain and the noise and irrelevant data are filtered out. So, these can be also described as a feature extraction algorithm. Now, an autoencoder network is actually a pair of two connected neural networks, an encoder as we see on the left and a decoder as we see on the right. An encoder network takes in an input and converts it into smaller, dense representation, while the decoder network can use that dense representation and convert it back as close as possible to the original input. Now, moving on to what are VQVAEs. At the heart of most generative models lies a variational autoencoder. Variational autoencoders are powerful generative tools which have applications as diverse as generating fake human faces to producing purely synthetic music. Now, variational autoencoders by design are autoencoders, but they have one fundamental unique property that separates them from their vanilla counterpart, and it is this property that makes them so useful for generating models. That is, their latent spaces are by design continuous rather than discrete, allowing them easy random sampling and interpolation. Now, what this means is rather than the bottleneck outputting static encoding vectors of fixed size, it outputs two vectors, a vector of means and another vector of standard deviation. Now, this allows us to introduce random samplings into the model before sending the vector to the decoder. Intuitively, the mean vector controls where the encoding of an input should be centered around, while the standard deviation gives us the area. Now, the encodings can be generated at random from anywhere inside this circle. This allows the decoder to not just decode single specific encodings, but ones that slightly vary too, as the decoder is exposed to a range of variation. Now, this allows creation of new samples and new data, and hence, instead of the original image being recreated, this leads to the production of new music and new images. Now, VQVAEs or vector quantized variational autoencoders are just a variation of variational autoencoders that use vector quantization to obtain a discrete latent representation. This leads to faster processing and quicker results. Now, standard autoencoders learn to generate compact representation and reconstruct their inputs well. But aside from a few applications like denoising our autoencoders, they are fairly limited. Now, the fundamental problems with autoencoders for generation is that latent space they convert their inputs to and where their encoded vectors lie may not be continuous or allow easy interpolation. But when we're building a generative models, we don't want to prepare a replication of the same image we put in. We want to randomly sample from that latent space or generate variations of an input image from a continuous latent space. Now, this is where variational autoencoders are helpful because they provide a continuous latent space for random samplings, thus leading to generation of new samples. Now, moving on to what are sparse transformers. Now, the transformer in itself is a deep learning model introduced in 2017, used primarily in the field of NL. Like RNN, transformers are designed to handle sequential data, such as natural language, for tasks such as translation and text summarization. However, unlike RNNs, instance, transformers do not require the sequential data to be processed in order. For example, if the input data is a natural language sentence, the transformer does not need to process the beginning of it before the end. Due to this feature, transformers allow for much more parallelization than RNNs and therefore reduce training time drastically. Basically, a transformer is based on an encoder-decoder architecture, but each encoder and decoder layer makes use of an attention mechanism, which for each input weighs the relevance of each other input and draws information from them accordingly to produce the output. Each decoder layer also has an additional attention mechanism which draws information from the outputs of previous decoders before the decoder layer draws information from the encoding. Both the encoder and decoder layers have a feed-forward neural network for additional processing of the outputs and contain residual connect. Now, sparse transformers utilize what is called a sparse formulation, which reduces some of the overhead by recomputing the attention matrix from checkpoints during backpropagation, a well-established technique in deep learning. When done for the attention matrix in transformers, it means the largest memory cost becomes independent of the number of layers, letting us train networks with substantially greater depth than possible previous, resulting in networks with as few as 128 layers, outperforming shallower networks on benchmark tasks such as CFAR 10. This is accomplished by using something called sparse attention, where each output position only computes weights from a subset of input positions. When the subset is small relative to full set of inputs, this drastically reduces time complexity. Now, moving on to the exploration of one such case where such an approach is implemented, we will look into OpenAI's Jukebox framework. Now, what is Jukebox? Jukebox is an open source neural net framework by OpenAI Labs that generates music, including rudimentary singing, as raw audio in a variety of genres and artist styles. It can generate melodies, rhythms, instrumental symphonies, and full-fledged songs with lyrics. Trained using a curated dataset of 1.2 million 32-bit 44.1 kHz songs and augmentation. Now let us look into how the model has been constructed. Let us begin with compression to discrete codes. Jukebox autoencoder model compresses audio to discrete spaces using a quantization-based approach called VQVAE. But this VAE in its vanilla state suffers from hierarchical collapse due to use of successive encoders coupled with autoregressive decoders and require optimization. A few steps to achieve such an optimization is using random restarts, where we randomly reset a codebook vector to one of the encoded hidden states whenever it falls below a certain threshold. Another one is to maximize the use of the upper levels, which contain the least amount of noise, to separate decoders and independently reconstruct the input from the codes of each level. And to allow the model to reconstruct higher frequencies easily, we add a spectral loss that penalizes the norm of the difference of the input and reconstructions. The structure of the network consists of 3 levels of VQPAE shown in the figure, which compresses the 44 kHz raw audio by 8x, 32x and 128x respectively. This downsampling loses much of the audio detail and sounds noticeably noisy as we go further down the level. However, it retains essential information about the pitch, timbre and volume of the audio. Next, we move on to generating code from the latent representation. Here, we train the decoder model whose goal is to learn the distribution of music codes encoded by the VQVAE and to generate music in this compressed discrete space. Like the VQVAE, we have 3 levels of decoder, a top level prior that generates the most compressed codes and 2 upsampling priors that generate less compressed codes. The top level VAE models the long range structure of the music, and samples decoded from this level have lower audio quality but capture high level semantics like singing and melodies. The middle and bottom upsampling VAEs add local musical structures like timbre, significantly improving the audio quality. Now moving on to the conditionings implemented on the data. Now we can provide additional information to the model. Now this has 2 advantages. First, it reduces the entropy of the audio prediction, so the model is able to achieve better quality in any particular style. And second, at generation time, we are able to steer the model to generate in a style of our choosing. This way, the model can segment music in genres in an unsupervised fashion. Some examples of conditioning we can implement on the data is genre conditioning, artist conditioning, and lyrics conditioning. Now note that in order to be able to control the generative model with lyrics conditioning provides more context at training time by conditioning the model corresponding to each audio segment. allowing the model to produce singing simultaneously with the music. Moving on to some of the limitations of this model. Now, while this is a big step forward in musical quality, coherence, length of audio sample, and ability to condition an artist's genre and lyrics, there is a significant gap between these generations and human created music. While the generated song shows local musical coherence, follows traditional chord patterns, and can even feature impressive solos, we do not hear familiar large musical structures such as choruses that repeat. The downsampling and upsampling process introduces discernible noise. Also, training and rendering might take huge periods of time, for instance, 9 hours of training for just 1 minute of musical data. Thank you.